So this week we're playing around with polar coordinates. We just finished up our law of sines and law of cosines, and those are important. And the big thing we're going to look at today is what does polar mean? And I added some resources here additionally. So I have a link to polar paper here. You do need to practice graphing by hand some polar stuff, and you can just do it on a plain piece of paper, kind of like we've been doing before with triangles and angles. But it's kind of nice to have polar paper. So that page there has two things. Has a link to a website I like to use if I need custom graph paper. And excuse the ads. They have cool stuff otherwise. And so here they got a polar graph paper generator. And if I just go with the defaults they have set here, that's going to give me this PDF right here. And then I can just send that over to my printer. It's one huge polar grid on a piece of paper. Let's close that. So you can play around with how many concentric circles there are and how many spikes there are primary and how many spikes there are secondary. And then you can do radians or degrees on there too if you want to. And then based on these settings here, this programmer put a bunch of sample graphs down here. So by just changing the settings above, you can get these different versions here. So like this one's kind of nice here. I think, is that the radian or degree one? Except for the ads, sorry. Okay, so that's the degree one. I guess the one that said radians is the one I want. So if you're still struggling with locating radians, this is a good one right here. You could print out. And then they had another one with even more radian measures. I think it was this one. Yeah, this one right here. 180 spokes with a whole bunch of radian measures. I think there's what, 48 coming around here. So that's kind of a cool one too. Different pi overs, pi fractions. So this is a cool website to either create your own, use their default, which I'm going to use today, or grab one of those other ones. And then this is that default one here, if you want to just grab that one and send it to your printer. And then I found another website that had different polar paper. If you just search around for polar paper or polar graph paper, you'll find a ton of websites that have stuff you can just grab and print. And for some reason, Canvas has been glitchy on me there. So let's just close that. Anyway, it's a lot like the first one I showed. It just has two graphs, one above the other on a regular sheet of paper. Okay, the other thing that's going to be useful for playing around with polar is doing this on a calculator. So I set up a couple of things for us to play with. So on this next page, polar coordinates in GeoGebra and Desmos, I have this embedded one here. And if the tools or the algebra panel are in your way here, just click it and that'll go away. It'll slide away and then you can see what I did here. So I have examples of how to do polar points in GeoGebra and how to do a polar function in GeoGebra here. And so you can either play with it in our Canvas screen or you can pop it out into a new screen here and then play with it here. And if you go to the algebra panel here, then you can see that I plotted this point A right there. And GeoGebra's notation is if you see a semicolon, that means it's polar. If you see a comma, then it's rectangular, like XY. And I'll go over that some more in a second. So we'll come back to this. Whoa, don't scroll there, scroll out here. And then I have another sample polar grapher for GeoGebra we'll look at later. And then there's also a friend of mine built this one in Desmos, and we'll check that one out later. Otherwise, we have the usual stuff, link to the textbook, link to the videos, link to the homework. So let's just do an overview of polar in my notebook. So polar coordinates are just a different way of plotting things on a plane. So we're used to Cartesian coordinates, which is this grid over here. Cartesian coordinates are also known as rectangular coordinates. And that's where we have two perpendicular straight axes. All right, so we have a y-axis here, let's say an x-axis there, and we plot points in this coordinate system xy like 2, -3 by just going over to x equals 2 and finding y equals -3 and then graphing that point, right? So there's the point 2, -3. So you've been doing that for years and years and years now. Polar you may not have seen before. Now polar goes back to our trigonometry training. And in trigonometry, we measure angles from the positive x-axis here. And then we have our what we call the origin over here. Right, so that's my origin. Over here, that origin is called the pole, AKA origin. And then I identify points in the polar grid by finding a radius and an angle. So let's suppose this is going out concentric circles, 1, 2, 3, 4. So this one right here would be a radius of 3. This one right here would be a radius of 2. That would be a radius of 1. Right? So think about this right here. We have R, and R is really concentric circles. Concentric circles. So if somebody says, hey, I get this polar situation and I know R equals 1, well, that's anywhere on this inner circle right here. If R equals 2, it's anywhere on this second circle out here. So to identify a point in polar coordinates, you need to give both R, a radius. I like to put a semicolon to indicate I'm talking about polar and a comma to indicate I'm talking about rectangular. And then I give my angle theta. So suppose I said I have the point 3, semicolon, pi over 4. Right, so 3 is my R, I'm somewhere on this circle, and then sweeping up, I just find pi over 4. Pi over 4 is right in between 0 and pi over 2 up here. So right in the middle, that looks like this one right here. So from that angle, I want that point right there. So that point right there would be my point 3, semicolon, pi over 4. Now in my notes, I like to put a semicolon. In the homework system, you're just going to write a comma. So a lot of times you're just going to see 3, comma, pi over 4. And by context, you're supposed to then just know, oh yeah, that's a polar point, because the problem said that's a polar point, not a rectangular one. So you got to really focus on the context, whether it's referenced as a rectangular Cartesian point or whether it's recognized as a polar point. So I can identify any point on the plane by giving a radius and an angle. So let's find another one out here. For example, suppose I had the point 5, -3 pi over 2. All right, so 5, so 1, 2, 3, 4, 5, somewhere on this circle here. And then -3 pi over 2. So I got to go around in this direction clockwise. So 1 pi over 2 would be down here. 2 pi over 2 would be at pi. 3 pi over 2 puts me up here. And I got to get on the right circle. So 1, 2, 3, 4, 5. So that would be right there. 5, -3 pi over 4. I'm going to use my semicolon notation like GeoGebra. Now, interesting thing about polar coordinates is there are many ways to get to any particular point, like this point right here. Let's highlight that one. I could have gone around in a negative direction to get to that point right there. So what would that be? Well, if I count around in the negative direction, I would have over here would be -1 pi over 4, -2 pi over 4, -3 pi over 4, -4 pi over 4. -5 pi over 4, -6 pi over 4. So this angle right here is also -7 pi over 4. So I could also call this point 3, -7 pi over 4. So in rectangular coordinates, there's a unique way to represent every single point, like 2, 3. There's no other way to get to that point besides saying x is 2, y equals -3. In polar coordinates, because we can keep revolving around and around and around in a positive direction or a negative direction, there are many angles that will lead to the same point. Now it gets wackier though. So here's the wacky part. Consider the points with a negative radius. So -3, semicolon, let's see, negative 3 pi over 4. Okay, so let's consider the angle before I consider the negative radius here. Negative 3 pi over 4, so that would be 1 pi over 4, 2 pi over 4, 3 pi over 4 in a negative direction. So that puts me on this spoke right here. That spoke right there is theta equals negative 3 pi over 4. Now, if the radius were 3, then that point would be 1, 2, 3. It would be right here. So that point right there is positive 3. Angle positive negative 3 pi over 4. If positive 3 is to follow that angle and then go toward that angle from the origin, then a negative radius must mean go the other way. So this point right here is also negative 3 pi over 4. So there's basically infinitely many ways to reference any point. Now, often there's the simplest way, which is a positive radius and an angle between 0 and 2 pi. That's the simplest way, but there's many otherwise. So simplest polar points. We would want r to be greater than 0. So 0. And we want theta to be between 0, could be 0, and up to, but not pi over 2. So that would be the simplest point. So if somebody told me, hey, I'm looking for a point, negative 3 pi over 4, I can definitely plot that. I can find where negative 3 pi over 4 is, and then I can go back through the pole, negative 3. But then I can come back and say, well, a simpler way to reference that point would just be 3 pi over 4. So we've learned about that kind of idea from our other basic trig on a circle. So polar is just a different way of representing things. And you may ask, well, why would we bother with polar? This seems a little nuts. Well, it's not. It's super, super important in many physical ways. So let me give you a quick preview of that. Radar. So radar is a way of using radio waves to track objects in space. And so here is a commercial radio antenna here revolving around, sending out radio waves in all directions. And what happens is there's a receiver there too. And so those radio waves hit something and bounce off. And then we can measure both the distance the radio wave traveled and bounced back, and we can also measure the angles that lead to that point. Now in three-dimensional space, we need 2 angles and a radius to get there. So we're just going to worry about in 2 dimensions instead of 3 dimensions. You may have seen in movies, TV, something, these scopes where things are being tracked, where this radar is revolving around and around, and it's identifying objects out in space here. And again, when those radar waves bounce back, we are able to calculate the angle vertically, the angle in the circle here, and then the radius away, which gives us a specific point in 3D space. And it's often used, it comes in most circumstances in aircraft tracking, for example, but it has lots of other uses besides aircraft tracking. And you can see here, this is kind of that idea of this central point from which we're tracking, and then we're rotating around to find things. And so in 2 dimensions, we just need that radius from the pole, from wherever the radar waves start, and then we need the angle from some position, usually the positive x-axis, and we measure away from that. So those are some examples there. Next big thing is the relationship between rectangular and polar systems. So again, polar, we have a pole, some point. And then we have a place, a line to measure angles from. So that's usually what we call the positive x-axis, right? But we have that reference line to measure angles from, and we measure angles counterclockwise as usual. And so then I have some point out in space. So let's suppose I have this point right here out in space. Now that point is going to be identified by r. I'm going to use a semicolon theta, but we'll often just see r comma theta for reference to a polar point, and we just have to know that it's polar, not rectangular. To get that point, again, r is my distance from the pole, my radius, and then my angle theta is this angle right there. Now, we also know that we can track points like this by having a vertical distance and a horizontal distance, right? So my y and my x. And if we compare the r theta to the xy, we make a right triangle. What do we know about this right triangle? Well, we learned very back in the beginning of this course that the x value is equal to that radius times the cosine of theta, and the y value is equal to the radius times the sine of theta. And so if somebody says, hey, I have the point 3 pi over 4, we could plug in the 3 and the pi over 4 here and here, and that would tell us what x and y are. So we could think about these two equations for points as converting polar to rectangular. Rectangular is also called Cartesian. And then I could take it the other way. Other relationships we have in this picture is the Pythagorean theorem, right? X squared plus y squared equals r squared. So we could say, solving that for r is the square root of x squared plus y squared from the Pythagorean theorem. And then as far as theta, we know that the tangent of theta is y over x. So theta must be the arctan of y over x. And this means given an x and a y, we can find r and we can find theta. Now, arctan only knows about angles between negative pi over 2 and pi over 2. So if that angle is in a different quadrant, then we would have to do some circle symmetry to figure out what angle that is. So again, don't forget that arctan only knows theta between negative pi over 2 and pi over 2. It only knows about those acute angles, positive and negative. So if we need an angle that's beyond this range here, like in quadrants 2 or 3, then we'd have to draw a picture and figure out what that angle is. So just the arctan alone isn't necessarily enough, depends on the angles. But again, this is set up right here for points to allow us to convert, in this case, rectangular to polar. So for example, earlier, I had the point, was it 3, 2 in rectangular? And I want to convert that to some polar points. I'm going to use my semicolon notation. So to do that, again, this is my x and that is my y. If I look over here, plugging in x and y here is going to give me the r that I want here. Plugging in x and y here is going to give me the theta I want here. And I just got to double check, is this in a quadrant that the arctan knows about? And just a reminder about that, picturing that on the unit circle. Theta to negative pi over 2 is over here, and theta to positive pi over 2 is over there. So the arctan only knows about quadrants 1 and quadrants 4, and quadrant 4, it only knows the negative version of that angle, not the positive version. So we always have to keep that in mind, be conscious of what quadrant we're in. So then to figure out what point this is in polar, I would just say, well, r is that square root, 3 squared plus 2 squared. So that would be square root of 9 and 4, square root of 13. And then theta would be the arctan of y over x, 2 over 3. And it's not a special angle, so I have to whip that out on a calculator. Let's get a new calculator because I need those other ones for something. Let's try, let's see, I've been using, oh, let's do Desmos. Graphing. So I wanted to know, let's see, square root of 13. So about 3.6-ish. And then arctan of 2 over 3. And so that gives me a radian angle of 0.588 And if I wanted, let's give that a name. Let's call that T for like theta. And if I wanted that in degrees, I would just take T times 180 over pi or switch the mode. So that would be around 34 degrees-ish. So I have this radius is about 3.6. And then I have this is about 0.5, is it 588? 588 or 33.7 degrees. And if you check out my picture here, I think I kind of tried to draw that. So let's see, if I say this right here is 1, 2, 3, and that's 1, 2, then that right there is my point 3, 2. So 3, 2. And then this angle right here should be about 33.7 degrees, and that seems reasonable. It's definitely less than 45, right? So draw a 45-degree angle in here, that would be right there. So that's 45, that's 33.7-ish. And then as for its length right here, well, X is longer than Y, the radius has to be the longest side here, so it's got to be bigger than 3, so 3.6 seems reasonable in that picture. So I've just calculated that the rectangular point 3, 2 is equal to the polar point, or at least approximately here, 3.6, I'm gonna use the semicolon, 3.6, and then I'm gonna use radian, 0.58 radians. And so again, we can switch back and forth. Another example of that would be to take, say, this point right here, 3 pi over 4, and convert that. So let's say we got polar, 3 pi over 4, and we want to convert that to rectangular, xy. And so in that case, I have that other set of formulas where x is r cosine theta, and y is r sine theta. And so we're going to get 3 times the cosine of pi over 4. Cosine of pi over 4 is square root of 3 over 2. So I get 3 square root of 2 over 2. And then 3 times sine of pi over 4. So that's going to be 3 square root of 2 over 2. And we can check that on the calculator to see if it looks right in the picture. Oops. So I'm getting it's a little bigger than 2, 2.12. So let's look back at the sketch, see if that seems reasonable. So I think this point in rectangular is approximately 2.12, comma 2.12 for x and y. And the picture if we were to trace this point right here down, straight down here, you can see it is just a little bit bigger than 2 there. So that seems reasonable. All right, couple of other things with respect to polar and rectangular. Why use one over the other? So pros and cons. So think about circles and rectangular coordinates. The unit circle which is like the easiest circle there is, has a complicated equation, x squared plus y squared equals 1. Now you in your life have seen a lot more complicated equations than this, but the first time you saw this, this was pretty complicated. We have both x and y squared here. And the other thing to consider is this is not a function in rectangular coordinates, not a function. If I wanted to graph this on most calculators, newer ones can actually graph it as it is, we would often have to solve for y, and we get y equals plus or minus the square root of 1 minus x squared, which is really two functions, right? The top part, y1, square root of 1 minus x squared, and the bottom part, y2, y equals negative square root of 1 minus x squared. So in rectangular coordinates, the simple unit circle is complicated. However, in polar coordinates, it's wicked easy. So the polar unit circle is just r equals 1. Since I didn't mention theta here, theta can be absolutely anything as long as r equals 1. So looking back at my polar grid, so let's get a new one to play on. And I'm just going to shrink that down a touch so it fits here. If I go with the same scaling before, r equals 1 is this circle right here. Right? So what was super complicated in rectangular is super simple in polar. So polar has its advantages in a lot of different ways. Rectangular has its advantages in a lot of different ways. And so it turns out in future mathematics, sometimes we will choose to work in the polar coordinate system because the problem is just way easier to work with, way simpler equations to deal with. And other times we want to deal with rectangular because rectangular is easy. So for example, check this one out. Y equals 2x plus 1, super simple rectangular expression, right? This is like the first kind of thing you learn to graph in algebra. So simple rectangular function. What would this look like in polar? So to graph this in polar, I have to get rid of the y's and the x's. And so our tools for doing that is we know that x is equal to r cosine theta. We know that y is equal to r sine theta. Other tools we have to work with are r squared equals x squared plus y squared, and the tangent of theta is equal to y over x. Oops, that's not an x. And I had written these two slightly differently before, right? Solving for theta and solving for r, but I'm going to use these versions. Now, when I'm using equations, not points, I want to get rid of y, and this one right here tells me how to replace y with r sine theta. So over here, to change this to polar, I'm going to replace that y with an r sine of theta. Equals 2, instead of an x, I'm going to replace that with what x equals here. R cosine of theta. And then I have the plus 1 out there. So now I have a new equation that has no x's and y's. And usually with polar, we write r as a function of theta. So next I'm going to solve this for r. So let's see, there's r's on both sides, so I got to get them all to one side. So I'm going to bring this over to the other side with subtraction because it's connected by addition. So I'm going to get r sine theta minus 2r cosine theta equals 1. And then I can factor r out of this difference. That's going to leave r times sine of theta minus 2 cosine theta equals 1, and then I can divide by that multiple to solve for r. So 1 over sine of theta minus 2 cosine of theta. What's my point here? My point here is what was simple in rectangular, 2x plus 1, is complicated in polar. So if I need to work with just straight lines, y equals mx plus b, I want to do it in rectangular, not polar, right? This is way more complicated a function to deal with. I have a rational function. I have sines and cosines in the denominator, okay? This will just graph that line right there in a strange way. However, if I need to play with circles centered at the origin, it's way easier in polar than rectangular. So again, they have their pros and their cons. So next we'll take a look at some polar functions.